Hello everybody and welcome to another math video. In this video I will be going over future value of an annuity and sinking funds. So how this video will be laid out is I will go over some vocabulary. I will distinguish what makes annuities different from what you've learned already, or maybe what you know already concerning compound or simple interest. And then I will go over the future value of annuities and then what a sinking fund is. As you can see here, they are going to use the same formula, but they have different goals in mind. So I can't wait to get into that. Let's get it. Vocabulary. Super important to understand what you're working with before you start working with it. Even in math, yes, vocabulary important. So here it is. I have 4 vocabulary words and phrases that I want to go over. The first of which is annuity. Annuity is any sequence of equal periodic payments, PMTS payments. So the payments have to be the same amount every time, and they have to happen at the same time length every time. So for example, a paycheck, a salary paycheck with no overtime, no nothing, would be an annuity. If you get paid, I don't know, $3,000 every 2 weeks, and that's your salary, and you cannot work overtime, you cannot earn any extra money, then you know for sure you're going to be getting $3,000 every 2 weeks, $3,000 every 2 weeks, every 2 weeks, every 2 weeks, over and over and over and over and over. And that's what an annuity is. Another idea of an annuity would be paying a minimum payment on your credit card. So it's paying $30 to your credit card. Next month, pay $30 to your credit card. Next month, pay, and never missing a payment, of course, but paying it the same day every month. That would be an annuity. Or another one, an IRA, an individual retirement account. I, in real life, put $200 into an IRA account every single month. It's automatically withdrawn on the 15th of every month. So that would be an annuity. All right. Next, ordinary annuity. This is just to distinguish between all the different type of annuity that does exist out there. And we will only focus on ordinary annuities. And it's just an annuity where payments, again, PMTS, are made at the end of the time interval. So this in real life could be any utility payments. Your electric company cannot charge you for electricity until they know at the end of the month how much you actually used. It could be the same for cell phone. It could be the same for internet, all that stuff. They charge you at the end of the month. So here we go, future value. Future value is the sum of all annuity payments at the and the interest they earned. Of course, that would be at the end of the scenario. So if it happens for 5 years, well, then at the end of 5 years, all of the annuity payments that you made and the interest they earned along the way. And a sinking fund, which we'll get to a little bit later, but I'm going to define it now with everything else, is an account used for accumulating funds to meet future obligations or debts or savings goals. So like a very quick scenario would be you just had a baby, you want to save for this baby's college education because we all know that prices are going up. Then you want to have $50,000 saved for this kid when they're 18. How much money do you need to save per month if you get, I don't know, 4% per year? Like that's what sinking fund is. It's a future savings goal or a future payment plan that you are trying to meet, and you're trying to figure out what payments you need. All right, enough with the vocabulary. Let's get into the math. I like the math a whole lot more. Compound interest versus annuities. How are they different? Well, with previous examples that maybe you've seen before or learned about before, with compound interest, you put money into an account one time. You just open up an account, and for some reason, you have $47,000 just kicking around like you do. You let it sit without ever depositing or withdrawing any money for some period of time. So, that whole period of time, let's say, I don't know, you're saving for retirement and you're 18 years old and you have that $47,000 and boop, you just pop it into a bank account or a stock exchange or whatever, and you just let it sit there. And 42 years later, when you're 60, you withdraw all the money after that amount of time. And that really doesn't sit well with how real world works. This is where we enter annuities. So annuities allow you to pay the same amount into an account at the end of the same time interval. So I was explaining that already. It's like you can pay the same amount into a savings account at the end of every month. And you can pay the same amount into an IRA every single month. And then you do that for a set period of time. Again, if you're retiring, for years. If you're saving for a car that you know you want to buy in 5 years, then your time period would be 5 years. But the point is, this is something that makes so much more sense, is you keep depositing over a long period of time and it's more realistic. Y'all, I don't have $47,000 just sitting around, but I can save $200 a month. That'll get me there eventually. So this idea of annuities is actually much, much more realistic. And as you're about to see, the more realistic the scenarios get, the more difficulty can be put into the math equation. But what I think is still beautiful about this is that there is still math that can describe what you're doing in the real world. And when I say it makes the math more difficult, I didn't say impossible. It just said a little more difficult. So keep that in mind as we move on through some examples. Here is the equation to figure out the future value of an annuity. So if you've seen the previous videos, you know that there are a lot of similar notations and variables from those videos represented in this equation. The first of which being n and I. So again, n is the total number of compoundings in the time length, whatever the total amount of time is. And you can figure that out by multiplying the number of compoundings per year times the number of years that are available. I, from a previous lesson, is the interest rate per compounding period. And again, if you're not given I outright, you can divide the annual nominal rate by the number of compoundings per year. The only new notations here are payment, PMT, and future value, FV. So we can multiply the payment times all of this nonsense to find the future value of our annuity. Jumping right into an example, we're asked to find the future value of 360 payments of $150 each into an account with I equal to 0.005. And you'll notice that this is already given as a decimal. You could be asked to convert it to a decimal. In that case, I would be 0.5%, which you would have to convert to a decimal in order to use it in the equation here. So what would this scenario look like in real life? 360 payments. Usually, if you can muster up 360 payments, that would be once a month, which would be 30 years of payment, which is normally a full-on career, a length of a career, 30 years. And putting $150 into an account would be something akin to like saving $150 per month for retirement. This interest rate, now that we know, if I say 360 months, this interest rate would relate or scale up to a 6% nominal interest rate, annual interest rate. So this sounds like a person who is saving $150 per month for 30 years of his or her life. Well, let's see how much money they'll have at the end of it. So we can figure out the future value by substituting 150 in for PMT, the payment. We can then substitute 0.005 in for I. 360 is the total number of payments made, minus 1 all over 0.005. And that would give us the future value. So I would just suggest doing all of this in a calculator. You can figure out the fractional portion first, and then you can multiply by 150. So when you do all that, the final answer will be $150,677.26. Okay, is that good? I think that's a very fair question to ask. You see this amount of money here, you say, holy moly, I would not want to get to retirement and only have $150,000 saved up. At least I hope that's your initial reaction. You have to have a lot more saved up in order to retire these days. To answer this question, we have to look at how much money was actually deposited into the account. And to figure that out, it's pretty straightforward calculation. We just multiply the payment you make every month or every payment period and multiply it by how many payment periods you have. So 150 times 360 payments would give you a total amount of $54,000 total investment. Now I take a look at $54,000 total investment over 360 payment periods. Again, I'm going to assume these are months. It looks like your investment almost tripled over that time. And tripling is, well, that's really good. Almost tripling is really, really good. That's my opinion. So knowing this amount, or knowing this information, if you could put $500 a month into an account with this interest rate for 30 years, that would give you an even better retirement package. Okay, so we figured out this was the actual amount invested. This is the actual amount of money you'll have in 360 payment periods from now, 360 compoundings from now. How much money was made in interest over that amount of time? Well, the amount of interest is a very simple calculation at this point. We can take the future value and we can subtract the total number or the total amount of payments you paid into the account. So again, that's future value minus the payments. So here's the formula for how you can compute interest. It is the future value minus the payments times the number of compoundings. And in this particular case, when you subtract these two numbers, you'll get $96,677.26. And over again, if I assume that this 360 represents months, over 360 months, or more easily understood, 30 years, you made, or your money made, $96,000 in interest. That's a lot of money. That's just over $3,000 per year for you having to put in an additional zero amount of work to make that extra money. For you, this might be 2 years of extra income, salary income that you earned. for nothing. Just time made that money for you. Okay, enough about that. Let's move on to another example. For example 2, if you are trying to compute the payment based on some future value, some number of compoundings, and an interest rate per compounding period, you'll just use this formula here. And if you can recall the original formula for future value, it looks something like this: 1 plus I to the n minus 1 all over I. What we did was we multiplied both sides by I to cancel with this one down here. And then to solve for payment, we divided by this thing here, 1 plus I raised to the n minus 1. 1 plus I raised to the n minus 1. So this is how this formula over here was computed. We just multiplied by I to get rid of the fraction, and then divided by this to isolate the payment. So we would use this, and honestly, this is meant more for the sinking funds that we'll be talking about here in a little bit. On to example 3. Example 3 allows us to take a look at finding how many monthly payments. So in this formula here, we would be trying to solve for n. So the question is, how many monthly payments of $54 would you need to make into an account with an annual rate of 3% to get $992.93? With a second question, how much interest was earned? In order to best answer this question, I just went ahead and solved for n. And you may recall from previous videos that since the variable we are solving for is in the exponent, we will have to use natural logs to get that variable out of the exponent. That being said, again, I went ahead and did all the math, and this is yet another formula that you can use to your advantage when you need to know how many payments for future value. Now all we have to do is identify everything in the expression here. Let's see, we know the future value is $992.93. We know the payment is $54, and the annual rate, we have an annual rate. We have to do a little bit of figuring here. So the annual rate is 3%, which means I would be 0.03, and the number of compoundings per year, since we're doing things monthly, would be 12. And when you divide this out, you get 0.0025. So we know I is 0.0025. Fantastic. So we can substitute all of this in for the different values here. So we'll have the natural log of something divided by something else times that plus 1 all over a natural log of 1 plus. All right, so the interest rate is blue. This is 0.0025. This is 0.0025. The payment is green, so put the payment there, and the future value is red, 992.93. There you go. So you can substitute all of this into a calculator to get 17.999 months. And we would generally round this up to the next whole number because that is something you have to do. That's how time works with finance most of the time, is we just have to round up to the next number, whole number of months. So this would take 18 months to save for that $992.93. So how much interest would have been earned along the way. I've already done an example similar to this. To find the interest, we would take the future value and we would subtract the payment times the n, the number of months that we actually paid into the account. And when you do that, let me write that out here. That would be looking like this. So interest would be 992.93 minus the $54 times the 18 payments. This would yield you a whole $20.93 of interest. So it would take 18 payments and you would earn $20.93 in interest along the way, which is fine. 3% is not a lot of interest to be earning over a year. $54 is not a huge amount of money to be saving, but maybe you're saving for a new TV or a new computer or something that you can get in 18 months if all you have is $54 per month to save. The last thing I want to say is that always with the units, 18 months, you can always convert things over into years. So with the 18 months, we could divide 18 by 12 because that's how many months are in a year. And we could get 1.5 years or 1.5 or 3/2 years, whatever makes the most sense for you in your situation at that time. Sinking funds. Generally, a sinking fund would be a non-retirement savings goal, like a house or a car down payment, home remodeling projects, new technology, like I mentioned in the last slide. It could be a TV or whatever. Basically, it answers the question, I want to save for fill in the blank. It costs fill in the blank. How much per whatever month, week, day should I save? And that's the general idea of a sinking fund. I suppose it could also be used for retirement goals, but I think sinking funds would be much more immediate than, say, a 35-year goal. Anyway, I digress. Example 1, I want to have $12,000 for a down payment for a new car 6.5 years from now. How much should I save per month at 5% annual nominal rate to reach my goal? And this is true. I just recently enough got a new car and I would like to start saving for another down payment already. How much would I have to save if I was putting money into an account that gave me 5% annual rate per year? All right, so we've got a little bit to figure out here. I have a future goal. I have we're trying to solve for payment. I'm going to remember that equation from the sinking funds example a couple slides ago. Here it is. So I know the future value already. That's fine. The future value is 12,000. The time, here we do have a time that's 6.5 years. But I want to know how much I should save per month. So I'm going to have to convert years over into months. Let's see. I have an interest rate here, 5%, but that's annual. So we'll have to do another division. And we can't do that division until we figure out how many months we have. Okay, this is going to be interesting. So let's see what we can do here. I'm going to start with the time because that is what we need first. So I know the total number of compoundings will be the number of compoundings per year, which is per month, monthly, times the number of years, 6.5. So n here would be, what would that be? 72 and 6 more is 78. Secondly, we have to figure out the I for this formula. I guess we didn't have to figure out n for that. I is the rate divided by M. Remember, M is the number of compoundings per year. So this is 5%, which is 0.05 as a decimal, divided by 12. And that is approximately 0.001666666666666. Sorry, got stuck on repeat there. 7. So now I have everything I need to just put it into this example, or this formula here. So the payment will be, let's see, this 1 plus minus 1. Okay, so the future value was in red, that's 12,000. The interest rate was in green, 0.0041666666666. Thank you. I got stuck on repeat there again. I don't know what's happening here. 4166. And you just have to type a bunch of sixes in here when you're figuring this out in the calculator. And then, of course, we cannot forget the exponent here, the 78. All right, so you just, again, I think you know the drill. Whenever you have some complicated mess of numbers like this, you should just use a calculator. And when you do, you'll see that you just need to save, or rather, I would like to save $130.51. I apologize, not 51, 52 cents per month. And then I can have $12,000, which hopefully will be roughly a third of the price of a car in the future. But this is it. This is the payment I would need to save per month. Good job, me. Now I'm going to go rework my entire budget to see if I can reach this goal. While I do that, I hope very much that this video has shed a little light upon how future values of annuity works, what they're good for, what a sinking fund is good for, and I wish you all good luck.